As we continue looking at techniques for finding derivatives, now we'll look at finding derivatives of the trigonometric functions. We'll start with the sine function. For the sine function, I want to remember a couple of limits that we looked at earlier when we were talking about limits. One of them is the limit as h goes to 0 of sine of h over h. We found out that that was equal to 1. Now, of course, we had a different variable there. I think we used x in that case. But, of course, the variable makes no difference as long as the h here, here, and here are the same, and the h goes to 0. So we know that this limit is 1. We also looked at another limit as h goes to 0. That was the limit of this quotient, 1 minus cosine of h over h, and we found out that that limit went to 0. So with that reminder, let us go ahead and see if we can derive the derivative of the sine function. Now, this is not a polynomial, so this is going to be different from what we've done before. So again, since we don't know anything about this derivative, we'll have to go to the definition. So the derivative, by the definition, is the limit as h goes to 0 of the difference quotient, and that's going to be the sine of x plus h minus the sine of x all over h. And as a notational note, you notice that when there's just a single variable after the sign, we usually don't put that in parentheses, so that's why I've left it off here and here. But I did use it here because it's more than one term that I wanted to keep together. All right, so there's the limit. Now, pulling upon something that you may or may not remember from trigonometry, which is okay, there is a addition rule for the sine, which allows us to break up the sine of x plus h into the sine of x, sine of h, and so on. And it turns out to be this. The limit as h goes to 0. On the top here, that sine of x plus h becomes, by that addition rule, sine of x times the cosine of h plus the cosine of x times the sine of h, minus, of course, the sine x here, which does not change, and then h on the bottom. So this is equal to this expression by the addition formula for the sine. Now, you don't need to know that right now, but we're using it so that we can complete this derivative. Now, notice here that the sine x is multiplied by cosine h here, and sine x over here is multiplied by minus 1. We're going to factor out the sine x and get this broken down into a couple of terms that we'll be able to find the limit of. So we'll take the limit as h goes to 0 now and clean this up a bit. The sine x, as I said, can be factored out. What's left is cosine h minus 1 on the top, all over h on the bottom. That's cosine h minus 1 over h. Plus, what about this term? Well, this term I will factor out the cosine x, and then what am I left with? The sine of h over h. Now, of course, you recognize both of these. This limit, as h goes to 0, goes to 0, and the second limit, as h goes to 0, goes to 1. That means this first term is 0, and the second term is now just cosine x. And lo and behold, we have discovered that the derivative of the cosine, of the sine rather, is simply the cosine. Nice and simple. In fact, we can write it out as a rule. We can write the derivative of the sine of x equals the cosine of x, as simply as that. Now, the other rules for the other trig functions, for example, starting with cosine and moving on to tangent, secant, and so on, are more complicated, and we'll get to those next. But before we do that, let's look at one example where we get to practice this new definition, or this new derivation. So the derivative of x times sine x. Suppose this is the problem posed to you. The only thing that's different here is that instead of sine x being alone, this is a product, of course. So you have to invoke the product rule, which we've done before. The product rule says leave the first factor, x, alone, and multiply it times the derivative of the second factor. We just found out the derivative of sine x is cosine x. So I'll write cosine x here. Plus, and we reverse that process, we leave the second factor alone, times the derivative of the first, and the derivative of x is just 1. So we end up with x cosine x plus sine x. And that is an example in which finding the derivative of sine x can be useful. And of course, you can have more complicated problems than this. But let's stop there, and then we'll come back and look at derivatives of the other trig functions. Now on to the derivatives of the other trigonometric functions. First of all, let me just mention that likewise, that is to say like the sine function with almost the same derivation, the derivative of the cosine function turns out to be minus the sine of x. So this is different from the first one. The first one was the derivative of the sine function is the cosine. Here the derivative of the cosine is the sine, and be careful, the minus sign is part of this, and that's something that people tend to forget when they first see this. Now, let's go ahead and derive another one just to show you how these might be done. I won't do all 6 of the trig functions, but let's look at the tangent of x and find its derivative. Now the tangent of x, luckily, can be written as a quotient. This is the derivative of the sine of x over cosine of x. And this is, as I said, a quotient, so we can invoke the quotient rule, and we will do that. What does the quotient rule say? It says you return a quotient. On the bottom, you have cosine x squared, and I'll write it this way, cosine of x squared. And then we start off the top with the cosine of x because that's the bottom, times the derivative of the top, which we just learned was cosine x also. So I'll put that here in parentheses. Minus, that's part of the quotient rule. Then we reverse the process. We started with the bottom times the derivative of the top here. And now let's take the top times the derivative of the bottom, and the derivative of cosine x is right up here. That's minus sine x. So there is our application of the quotient rule. This is the derivative. Let us simplify it so we can see what's going on here. The first thing you should quickly notice is this is cosine squared minus this expression. There's another minus here, so that's going to be plus, and this is sine squared. You may remember your identity that sine squared x plus cosine squared x is equal to 1. And that's exactly what we use here. The top simply becomes 1. The bottom stays cosine of x squared. Cosine of x squared, 1 over cosine x is equal to secant x, so 1 over cosine x squared becomes secant squared x. And although this is the traditional notation for a trig function that's squared, it is often better to rewrite it as secant of x quantity squared to be absolutely sure that you see where the square is. And that gives you the derivative of the tangent function. Now what about the other trig functions? Well, the cotangent, the secant, the cosecant can all be calculated in this manner by going through the derivative and coming up with the result. Those are good exercises for yourself. What I'm going to do here is ask you to observe a pattern, because you'll need to memorize all 6 of those trig function derivatives. So it helps to have some sort of a pattern to remind you of what the relationships are. Let's write down what we already know here. The derivative of the sine of x is equal to the cosine of x, and I will pair that with the derivative of the cosine of x, which is equal to the sine of x with a minus sign out front. Again, there's that minus sign. Now, let me go ahead and on the right-hand side here, write the new one that we just computed, the derivative of tangent of x, which is secant squared x. And now let me show you the derivative of the cotangent of x. And you'll begin to see the emergence of a pattern. The derivative of the cotangent of x is going to be the cosecant squared with a minus sign. So it's minus cosecant squared of x. That should remind you of what happens over here. The derivative of the sine was cosine, and the derivative of cosine was the co-function to that, which in this case is sine with a minus sign. So here's a minus sign here. Then if you go ahead and look at, say, the secant of x and take its derivative, that will be secant of x times tangent of x. And if you had to guess what the derivative of the cosecant of x would be, by now you should have some sense what the answer might be. You'd expect there'd be a minus sign, and that perhaps you'd have the cosecant of x times the cotangent of x. And if you write that down, you're absolutely correct. That is the pattern I wanted to point out here. If you know basic derivatives, like sine and cosine, for example, tangent, and secant, as the derivative has derivative equal to secant tangent, then you can immediately find the co-derivatives by taking the original derivative, taking the co-functions, and putting a minus sign out front. And of course that works backwards. If you have this derivative and you take their cofunctions and a minus sign, you're back to this one. So there's a nice pattern among these six, and if you practice this enough, you're going to find it's not too hard to memorize, which is something you definitely want to do with these functions in order to function yourself in calculus. Let's look at an example now where we get to use some of this. Here's an example. Suppose we take a very simple trigonometric function, no complications. We'll just take the secant function. And we will ask the question, find the second derivative at pi over 4, which is the 45-degree angle, of this function. All right. How do we go about doing this? Well, we have to get the second derivative, so let's do that first. Here is the original function. Let's write that down for clarity. Secant of x. Then we've already seen on the previous page that the first derivative of the secant function is secant of x times tangent of x. But we're asked for the second derivative, so we need to take the first derivative of the first derivative to get the second derivative. That is going to be, let's move it over here so we have a little more space. That is going to be, this is a product, so we will follow the product rule. We'll leave secant of x alone times the derivative of tangent of x. And tangent of x is secant squared x. So there's the derivative of the tangent. Plus, we reverse the process. Tangent of x times the derivative of secant, which you may remember from the last page, is secant of x times tangent of x. So that would be this derivative over here. Then we can simplify this a bit. Always a good idea whenever you're working to see if there's some simplification you could do. I notice there's a secant common to both of these, so let me pull that out front. And then I'll have secant squared x plus tangent squared x. And there's nothing particular I can do with that, so let me leave that for the moment. Now, I have the second derivative. I need to calculate the second derivative at pi over 4, so let me start doing that. I want to remind myself of what the trig function values are at pi over 4. So let me do a quick reminder. Let me draw a line here so I can separate this off. Recall, and I'm doing this to help you remember how to remember these sorts of things. This might be called a mnemonic device. If you have a right triangle which has both of its legs equal to size 1, then each of the angles in here is pi over 4. I'll only mark one of them. And of course, the hypotenuse has length square root of 2. So what I do is I remember, I say to myself, I'm interested in finding, in here I will need to know the secant and the tangent to calculate this second derivative. So I'm interested in finding the secant. I remember that the secant is 1 over cosine, and cosine is one of the ones I remember as the adjacent over the hypotenuse. So the cosine is 1 over square root of 2, which makes the secant square root of 2. Likewise, I remember that the tangent is the opposite over the adjacent, or the sine over the cosine, and in that case, I'm going to get 1. So, with that reminder, that little trigonometric interlude reminder, I can now move from the second derivative in general to the second derivative at pi over 4, the angle I'm interested in. And here is my formula for the second derivative. I need to put in the secant, which I've just learned is square root of 2. Then I need here secant squared, so that's going to be 2, that's nice, plus tangent squared, which is 1, that's also nice. So I end up with 3 times the square root of 2, and that's exactly what I was looking for. That is the second derivative of this function evaluated at pi over 4. Now, in this process, I used my knowledge of the derivative of the trigonometric functions, my knowledge of the product rule here, my knowledge of trigonometry, and sometimes you have to remind yourself of it. That's why we did this. So we'll stop there, and then we'll come back with some applications. As promised, here are some applications. The first application is very standard, but let's practice it anyway. Suppose we have here the ground, and of course mathematical ground is always just a straight line. And suppose here we have a flagpole. And this flagpole is known to be 50 feet tall. Now, somewhere up here is the sun. And the sun is shining on this clear day. And so the sun, if you follow a path down here that passes through the top of the flagpole will cast a shadow, or the pole itself will cast a shadow due to the sun, which will be lying along the ground here. Let us label the length of this shadow S, S for shadow if you like, and that will be S in feet. Let us also mark the angle here, what the sun is making as it passes through the top of the pole with the ground. Now here is the question in this example. Find the rate at which the length of the shadow, that's that S value, the length of the shadow is changing with respect to the angle, theta, when theta is, say, 45 degrees. Now what we'll do in this problem is we'll immediately write theta equal pi over 4 in radians, because in most calculus problems you tend to work in radians rather than degrees, but you can always translate back to degrees at the end if you like. So, and we're looking for the rate at which the length of the shadow is changing. Now that assumes that the sun is moving in the sky, and as the sun is either going up or going down, this shadow will change in length. So how do we go about doing this? Well, we'll come back to this page, but let's move it out of the way for the moment and start a solution. First of all, when you read these problems, you should interpret the word rate to mean derivative. Or it should certainly imply that a derivative is going to be involved here. So that's a part to take note of. Then we are interested in finding the rate of change. There's that derivative again. The rate of change of S, the length of the shadow, with respect to theta, the angle. Now we have notation for that, and it's always wise at the beginning of these problems to write this down in proper notation. How do we write rate of change of S with respect to theta? Well, we simply write ds d theta. Now, we're not really interested in this general formula, although it may be useful later. We're interested in it evaluated at one specific point. We want the derivative of S with respect to theta at the point that theta is equal to pi over 4 or 45 degrees. That's what we're interested in. So, in order to do this, in order to calculate this derivative ds d theta, we need to have S written in terms of theta. So let me write that down. We need to write S, which is the shadow length, in terms of theta, which is the angle. So let's go back to our picture now to remember what we're looking at. Here is our picture. Here's theta, here is the length S down here. And the pole, if you remember, is straight up in the air, so that's really a right angle. Now somehow out of all of this, using my own knowledge of mathematics, I need to find a relationship between the variable theta and this other variable S. Now I think you'll see what it is. I will draw the triangle again so we can actually verify what you think. Here's the triangle, and if I separate it from the picture I can make it a little cleaner. Here's theta, here's that right angle, here's S, the shadow distance, and remember the pole is 50 feet high. With this in mind, I think it's easy to find a relationship between theta and S. It's going to involve some trigonometric function. You could actually use many of them, but let's find the simplest one. This suggests we consider a ratio such as, say, the adjacent to this angle, that would be S, over the opposite. We're using these abbreviations for trigonometric relationships. The adjacent here would be S, the opposite would be 50, so this would be S over 50. Now what is the adjacent over the opposite? Well, that is exactly the definition of the cotangent of theta. The cotangent then is S over 50, the adjacent over the opposite. Now that pulls upon your knowledge of trigonometry from a right triangle. So that is outside the problem, but you need to have that basic knowledge. Now I'm interested in finding the derivative of S with respect to theta, so let me solve this for S. Let me put the S on this side, and I'll write S then as 50 times the cotangent of theta. Now all I need to do is find the derivative of this. So I'll do that on the next page. And I'll write the function s as s of theta, remind myself that it's a function of the angle, and rewrite it here as 50 cotangent of theta. And now I'll compute ds d theta as I wanted. The 50 is a constant, it simply stays out front. The cotangent of theta, you may remember, and this is where your memorization of these will come in handy, is going to be minus the cosecant squared of theta. Now again, this was not what we were looking for. We're looking for this derivative evaluated at one particular point. So that means the derivative with respect to theta evaluated when theta is equal to pi over 4 is equal to, let's see, I can rewrite this as minus 50, get that minus out front, and then I will have cosecant squared of pi over 4. So I will need to know the cosecant. Well, again, I'm going to quickly draw the triangle we've seen before in another problem. The triangle here, the 1, 1 triangle, where this angle down here as well as up here is pi over 4, and this hypotenuse is square root of 2. I remember that the cosecant is 1 over the sine, and the sine is the opposite over the hypotenuse. So the sine is 1 over square root of 2, which makes the cosecant square root of 2. And if I square it, I just get 2. So this becomes minus 50 times 2, which in the end is minus 100 feet per radians. Or you could say feet per radian, either way. And that is the solution to the problem as far as we're concerned. Now, if you want, and this is a good exercise to perform if you don't remember how to do it, you can convert to feet per degree if desired. And in engineering and physics, very often degrees are commonly used, so you should know the translation that takes you from radians to degrees. Remember, the basic idea is that pi radians equals 180 degrees. Now, I won't say any more than that. We'll move on to another example here, but keep that in mind if you're going to use these in applied situations. Okay, one more example. Show that this function y equals a sine x plus b cosine x is a solution of the following differential equation, y double prime equal minus y, and that's going to be a solution for all values of constants, a and b. So for all constants, a and b. Solution. Now, the reason I'm bringing this up is this is a famous differential equation, and it shows a natural relationship between the very well-known sine and cosine functions. And sine and cosine, of course, are waves, and they measure how things move up and down, and that happens a lot in physics. The solution, of course, is to check that this is true. I'll need the second derivative. I'll have to do that by starting off with the original function here, a sine x plus b cosine x, calculating its first derivative, which is a derivative of sine x, which is cosine x, plus b derivative of cosine x, which is a minus sine x, remember. And then the second derivative will be a times the derivative of cosine x, which is a minus sine x, plus b times the derivative, well, the minus will stay, derivative of sine x is just cosine x. So we want to see if this relationship between the second derivative and y holds. Is the second derivative just the negative of the y function? Well, we don't have to write this out. We can just look and see. Here is the y function. If I put a negative throughout, I'll have negative a sine x, negative b cosine x. And isn't that exactly what I have here for the second derivative? Negative sine a sine x, negative b cosine x. So y double prime indeed equals minus y. This is a well-known differential equation, and it's a differential equation because it has derivatives in it. And as you talk about matters in physics and elsewhere, you'll probably come across this relationship, so it's good to see it once. More derivative rules. Now we ask the question, what if you have the composition of two functions? How do you take the derivative of that? Well, that's what we'll look at now. That's called the chain rule. Derivatives of compositions of functions. Before we just write down the rule, let's examine a motivating example. And afterward, be sure and tell your instructor whether it was motivating. Okay. Find the derivative with respect to x of x squared plus 1 to the 100th power. Now, what kind of technique do we have so far? Our only technique so far is to multiply this out. Well, that's a power of 100. That's tedious. No one wants to do that. There ought to be some easier way to find the derivative of this function, rather than multiplying this out and getting a very, very long polynomial and then just computing the derivative step by step. There ought to be something a little easier. Instead, as you may have guessed from the title of this section, let us think of the x squared plus 1 to the 100 function as the composition of two functions. The composition of two functions. And perhaps these functions will be simple enough that we can compute those derivatives and use them to compute the one we want. So let us suppose that we take one of the functions we're interested in to be the function that takes something to the 100 power. That would be f of x equals x to the 100 power. And let us suppose we look at another function, which is the function that takes x, squares it, and adds 1. With those two functions, then using what we know about compositions, f of g of x is equal to f of, well, what's g of x? There it is. Copy it down, x squared plus 1 equals. And now here's f, which is the function that takes things to the 100 power. So if f is acting on x squared plus 1, what does it do? It takes x squared plus 1 to the 100 power, which is exactly the function we started with. So first step, we have taken our original function and rewritten it as the composition of two functions, two simpler functions. And notice, if I wanted the derivative of these two functions individually, that would not be hard. These are just polynomials. Simple polynomials, as opposed to this one, which when expanded is a long polynomial. So that raises the question. Let's go ahead and write the question down. Can we use the easy derivatives of these two functions, x to the 100 and x squared plus 1, to calculate the derivative we are interested in? To calculate the derivative, and of course we are interested in the derivative with respect to x, and that will have meaning later, of the function y equal x squared plus 1 to the 100. Can we do that? Well, that's what we would hope that all this has been leading up to, and in fact we can. The answer then is yes, and here's how I can give you some motivation to believe the process. Let us rewrite our function as y equals x squared plus 1 to the 100. I'm writing it as y instead of f of x. That's going to be helpful. Now what do we want here? Let's just keep in mind what we're looking for. We want to find dy dx, the derivative of this function with respect to x. Now, let us rewrite this as the following. Let's write y equals u to the 100, where, of course, what have I done? I've let u equal the inside part x squared plus 1. So I've separated this out into an inner part, which is the u part, and then when the u is there, an outer part, which is the 100th power part. That's the key here. Because each of these derivatives, as I've already said, are easy to take. The derivative of y with respect to this variable u is 100u to the 99th power, and the derivative of u with respect to x, because it's a function of x, is even easier. It's just 2x. Now, with this dy du and this du dx, there's a notational suggestion being made here. This notation, and that's the reason this notation was invented, to suggest such things, this notation suggests that we multiply these two derivatives, just plain multiply them. Multiply to get what we want. That is to say, we're looking for dy dx, and if you, for the moment, think of these as actual fractions, as the notation suggests they are. Now, we don't think of them that way. We really think of this as d bar du acting upon the function y, and this is d bar dx acting upon the function u. But if you'll allow me for a moment to think of them as fractions, which the notation suggests, then if we multiply them, look what happens. dy over du times du over dx. Apparently the du's cancel, leaving us with dy dx, which is exactly what we wanted. In fact, this can be proven true. Now, we won't do the proof, but we can actually prove this. So what is apparently true from looking at the notation is in fact true for the three derivatives. Later in this course, we will actually define what it means for these dy and du's and dx's to have meaning. But right now we won't. Let's write down what we've just learned. First, to remind us of what we've got, remember we have a composition of two functions. So x going to g of x is the g function, and then f going to then f acting upon g of x is the f function. Together, they form a composition which in the notation we've used before would be f composed with g, written this way, because the g is done first and then the f. Now that's just there to keep in mind what we're doing. Remember, we let the g of x, which was the inner function, equal u, and this final function, this entire composed function, is of course our original function, which we've decided to call y. Now I can write down what is known colloquially as the chain rule, and I'll show you why it's called the chain rule at the end. The chain rule, as follows. If g is differentiable, and again I'll abbreviate differentiable here for convenience, differentiable at x, and see g comes from x, so we're asking g to have a derivative x, and f is differentiable at g of x, which is u, so f here acts on g of x, so we'd want it to be differentiable back here on the numbers that it acts upon. Then y, which is this composition of two functions, is differentiable at x, because this is the entire function. It is now differentiable at the place where it starts. Where, and here is the actual calculation we just learned about, dy dx can be calculated by taking dy du multiplied by du dx. That is what we learned earlier, and we guessed, and in fact it's true. It is actually working. Sometimes this first derivative is referred to as the outer derivative, and the second one as the inner derivative. And you'll see why as we work ahead. But the inner derivative would be the one that the derivative of u with respect to x is this first derivative, the function that is performed first in the composition. And so it is inner in that sense. And this would be the outermost one. What is the reason that this is called the chain rule? Well, if you imagine there's a chain link here, du, there's your chain link. And so you can think of this as chaining along. And you can actually repeat this many different times if you have more functions. Now let's practice this. This rule will be completely used by you in almost every derivative you take from now on in this course. You want to get used to this. Here is the question I will ask in this one. Find the derivative with respect to x of the cosine of the quantity x cubed. So this is a composition of the x cubed function and the cosine function. And we'll keep it simple. Let's just see what the chain rule would give us here. Well, first of all, so I can remember the chain rule, let me rewrite this. Write the function as y equals cosine of x cubed. That's just for convenience, but it's helpful. Now let's point out the inner and the outer functions here. This function here, x cubed, is the u function. This is the inner function. This is, if you like, the thing cubed function. You take something and cubes it. This outer function is the cosine function. So there's inner, there's outer. You can think of this as the cosine of box function. So we have the inner function and the outer function. Then by the chain rule, we can compute the derivative here, and you'll see how the inner and the outer are used. The chain rule says dy dx is equal to dy over du times du over dx. That, of course, is dy, or ddu rather, of y. Y is what? It is cosine of u if we replace the x cubed by u, times the derivative of u with respect to x. So derivative with respect to x of u is x cubed. These become, the derivative of cosine u is minus sine u. The derivative of x cubed is 3x squared. In all of these problems, you must always return to the original variable. The problem started with x's, it has to end with x's. So I will replace u here, u is x cubed. So I have minus sine of x cubed times 3x squared. And I am now done. I have computed the derivative of this function at the top using the chain rule. This is how you want to analyze these. Try to find an inner and an outer function, something that is done in order, because this is a composition of two functions. One has to be done before the other, and the inner one is the one that's done first. Let's do another example. Find the following derivative. Derivative with respect to t this time of the tangent 4t cubed plus t. Solution. Now, as you gain more experience in doing derivatives, you will not rewrite this in order to mention the u. You will just go ahead and take the derivative knowing what the u is. Let's see if we can do that here, and I'll talk it through. I want this derivative. This derivative involves an inner function, which I see here, which is the 4t cubed plus t function, and the outer function, which is the tangent of something function. So there's the inner and the outer. The chain rule says I'm supposed to take the derivative of the outer function first, ignoring what's inside. When you let this whole thing be u temporarily, that's what you're doing. You're ignoring any internal structure. So if I just think of this as tangent of something, what is its derivative? Well, tangent of something has derivative secant squared of that same something. So the outer derivative is secant squared of 4t cubed plus t. I'm only concentrating on the outer derivative, so the inside is left the same. Times, now I need the derivative of the inner function. The inner function is this 4t cubed plus t. That derivative is going to be 12t squared plus 1. And now I've applied the chain rule. This is now the outer derivative. And this is the inner derivative. And as I was saying, I've applied the chain rule without mentioning the u and introducing that letter into this problem. As you become more experienced, this is exactly what you're going to do. But even if you don't mention it, you're always doing an outer and an inner. And if there are several functions nested, then you might be starting out with an outermost and moving to the next outermost all the way to getting to the point of the innermost. That's something we can try a little later. The chain rule allows us to generalize some of our familiar derivative formulas. And that's what we'll look at now, generalized derivative formulas. And here is how that works. Since the derivative of f with respect to x by the chain rule is df du times du dx, assuming there's only one inner function, we can rewrite this using the same functions, but writing it with a little different notation, we can write d bar dx, which is what this means, of the function f of u, thinking f as a function of u. Then this second part becomes f prime of u, just the derivative of u, which of course it is, times du dx, which we will leave alone. Now in this form here, we can generalize some of our old formulas. For example, let's start with the simplest one that is a favorite of students. The derivative with respect to x of x to the n is equal to nx to the n minus 1 power. Now this is where n is an integer. We will extend that later, but we haven't done that yet. Let us now take this and extend this. Imagine that instead of x being taken to a power, an arbitrary differentiable function is taken to a power. How will that change the rule? Well, the idea is right here. If I'm taking the derivative of f with respect to u, some unknown but possibly more complicated than single letter function, then I get the derivative here, but notice that I have this second function here that must be multiplied by it. It's the derivative of the inside, because the chain rule demands that. So what would happen here if I took the derivative with respect to x of some u function which I don't know? It might be x, but it might also be more complicated. What should I get out of this? Well, you might naively say I should just get u n times u to the n minus 1, just as I did back here, but that would ignore the structure of u. So the chain rule says you must have the derivative of u multiplied by it in order to have the structure that is involved in this derivative. And of course, again, n is just an integer here. We extend that at a later date. And so we're not just tacking this on, we are actually following this directly from the chain rule. And it actually works back here too. If the function u is just x, what is du dx? That's dx dx. That's the derivative of x, which is just 1. So I could write a 1 here if I wanted, but we don't do that. In general, this is what happens when you take the derivative of an arbitrary function to a power. You get the same old rule that you had before, plus multiplied times the derivative of the function that's under here. Let's do one example so you can see how that works. Suppose I want the derivative of the secant to the 10th power of x. Now first, as I've warned you, it's better to rewrite this with really good notation, writing it as secant of x to the 10th power, rather than this traditional and not really very good notation. So having written it this way, I see that I have a u function here to a power. The generalized power rule says, first of all, I ignore the inside as I always do with the chain rule, concentrate on the power function first, and I get 10 times the secant of x to the 9th power. Then I concentrate on the inside and take its derivative. So I'll write that out. I need the derivative then of the secant of x. So that is 10 times the secant of x to the 9th power times, and if you remember the derivative of the secant of x, which you should, it's secant of x times tangent of x. And that is it. That is the entire derivative using the chain rule and this generalized power rule. Now, can we generalize some of the other rules we've seen? Sure we can, in exactly the same way using the chain rule. So I won't write all of these out, but let me mention a couple of them. Similarly, if you want the derivative of the tangent of u, where u now can be some more complicated function than just x, you would expect to get back secant squared of u, because that's the derivative of the tangent. The tangent of x has derivative secant squared of x. If it's u, however, you need to multiply it by the derivative of u, as the chain rule specifies. Then, of course, if you looked at, say, the secant of u, that derivative would be secant of u times tangent of u, which is what the original rule says. And again, because u might be more complicated than x, you multiply it times the derivative of that function, and so on. Every rule you learn in this course for x can be generalized using the chain rule to arbitrary functions u. So be prepared with that and practice this. Time for some exercises. The first one, is just a straightforward calculation, but it'll allow you to practice your differentiation rules. Let f of x equal the following function: x to the fourth minus the secant of 4x squared minus 2, all taken to the minus fourth power. And the question is simply to find the first derivative. It'll involve several rules, so I'll leave that to you to try. So, it's a derivative. And we've just been examining the chain rules. You probably expect that has something to do with this. So let's look at this. What we have is a function within the brackets taken to the minus 4 power. So it certainly looks like the composition of two functions. In fact, it looks like it might be the composition of more than two functions. But let's take it one step at a time. What we want to do is look at the outside function first. Now the outer function here is something to the minus 4 power. So when we write the derivative down, we will do that derivative first. That derivative says bring the power down, leave the inside, the entire complicated inside, untouched while we concentrate on the outside. And so it is the derivative of something to the minus 4 power is minus 4 something to the minus 5 power, because we subtract 1 from the power. Now I'm going to have to go down here, put a dot for multiplication. Now we look inside. Inside we have this difference, so we can calculate 4x cubed minus, as the derivative of the first one, minus the derivative of the second. But notice the second is itself a function that's a composition of two functions. So that doesn't throw us. We simply say, look, I will have now applied the chain rule here. And the chain rule here says first take the derivative of the outer function, which is the secant function in this case. So that will be the secant of 4x squared minus 2. We don't do anything with the inside yet, times the tangent of 4x squared minus 2. So I'm taking the derivative of the secant of something, and I'm getting the secant of something times the tangent of something. Now, as a final step, I look inside to complete the chain rule down here and find the derivative of the inside. The derivative of 4x squared minus 2 is easy. That's just 8x. If I can slip that in here at the edge. So now I have completed the derivative of this function. I had the chain rule applying to this function overall, first concentrating on the outer function to the minus fourth power, and then the inner function, which happened to be in two parts, one of which involved the chain rule again. Many problems will be of this sort, so you want to learn to keep track of where you are, what's inner and what's outer, what you have to do at a given stage, and what it completes the derivative for you. Let's look at another example, one that has a different question and answers a different question. Find an equation. We've done these sorts of things before. Find an equation for the line tangent to the following function, y equals the tangent of 4x squared at the point x equals the square root of pi. So give that one a try. For this problem, we need to find the equation of a line, as we've done before. It's the equation of a tangent line, and as usual with the equation of a line in this situation, we'll need the slope of that tangent line and a point lying on that line. What we have here is the x value of a point on that line, and we'll have to compute the y value at some point. Let us first start with the hardest part, which is finding the tangent slope. The tangent slope, as we know, can be gotten from a formula for tangent slopes, and that formula is the derivative of y with respect to x. Now the actual tangent slope we're interested in is dy dx when x is equal to the square root of pi. So first let's compute dy dx, and then we'll evaluate it at square root of pi. So the derivative of y with respect to x is the derivative of this function, tangent 4x squared. This is another example of the chain rule. This is the tangent of an inner function, so we'll treat it the way the chain rule says. We'll do the outer function first. The derivative of tangent of something is equal to secant squared of something. So that's secant squared of 4x squared. The inside again is not touched at this stage. Times now the derivative, so this is the outer derivative, if you like. Let's go ahead and write that down. Times the inner derivative, and the inner derivative is the derivative of 4x squared, which is easy. It's just 8x. So this is the inner derivative. And we can leave it just like that, because what we're going to do is evaluate this at a certain point, so I don't need to do any simplification. I now will let x be the square root of pi and substitute that in here. If I do that, I get secant squared. Square root of pi here squared is pi, so this becomes secant squared of 4 pi times 8 times the square root of pi. Now I need to know the secant at 4 pi. So that involves thinking a little bit about what the secant function means. And you might follow some sort of argument like this. The secant function is 1 over the cosine function. So I really only need to know what the cosine of 4 pi is. And if you remember your unit circle, if I quickly draw a unit circle here, something like this, and you remember when you draw triangles in here, the cosine is always the horizontal distance here, the x value of the triangle, then when you're here at 0, or here at pi, or here at 2 pi, those are all where the multiples of pi are. Notice that the even multiples occur over here at 0, which means that the cosine has length 1 in those cases. If the cosine is length 1, that means the secant is equal to 1 also, and so this expression here becomes 1, and so this just becomes the 8 times the square root of pi. Now, whether you remember your trigonometric functions using the unit circle like this or some other means doesn't really matter as long as you can come up with them when you need them. So we have the tangent slope here as 8 square root of pi. We now need the tangent point. We have half of it, but not all of it. The tangent point, we have x equals the square root of pi. So we need to find y. Y is going to be the tangent of 4x squared, so that's the tangent of 4 pi. And quickly we can see that that's the sine of 4 pi over the cosine of 4 pi. Why did I bother doing that? Well, maybe you don't remember tangent of 4 pi, but you should remember that the secant, or the sine rather, of multiples of pi is always 0. So this gives you 0 as that y value for the point. So the point here is actually square root of pi, 0. Then finally we can write the tangent line with that information. And that would be y minus 0 equals 8 square root of pi times x minus the square root of pi. And if you simplify that, you get y equals 8 square root of pi x minus 8 pi. And that is the line we were looking for. And that finishes the exercises.